Okay. We're going to move on and look today at the binomial theorem. And initially, this is going to seem totally out in left field compared to what we've been doing. But there is a connection between the binomial theorem and what we're doing today and what we have been doing specifically with combinations. What we are learning today is how to expand a binomial raised to an exponent. So at the end of today, everyone, if I say to you, expand that, you may not like me for telling you to expand that, but you will know how to do it. And it will not involve the level of work that you might think it would involve. If I ask you at the end of today's lesson, if I had 3a minus 4b raised to the 7, I could ask you this. If you were to expand it, what will the fifth term of the expansion be? And you don't have to expand it to answer that question. Okay, that's what we're learning today. These are both binomials that are raised to an exponent. They're called binomial powers. So that's what we're going to start off with here. The expression x plus y to the n is a power of a binomial. What does that mean? It means we have a binomial raised to an exponent. Really basic, okay? Expand each of these. So what is it we get when we take that binomial raised to a power, or an exponent rather, of 0? You get 1. Anything to the 0 is 1. And I'm going to write my answer below, and I think that might be what you should do, unless you can write it above, below or to the right, but I don't know how much room you have. If I say to you expand x plus y to the 1, well, that's candy stealing territory from babies, right? Anything raised to the 1 is that same thing. If I say what is x plus y to the 2, I would say to you that I think it's reasonable to expect that everybody knows that's what x plus y to the 2 is. However, just to cover my bases here, boy, left field, bases. Let's see if I can find some more baseball analogies today. You need to take x plus y times x plus y, and that involves the distributive property, which we learn a shortcut for called FOIL, and you're going to get what we have. No problems there. If I say to you, what is x plus y cubed, things become more complicated because I have x plus y times x plus y times x plus y. So when you multiply three things, you multiply two of them, and then you multiply by the third. But that's okay because we already know this is x squared plus 2xy plus y squared. So all we need to do is multiply that by x plus y. And that's why I've kind of left a bit of room there on the right of this side on your handout, so you have some room to write your work. When I multiply things like this, this is the way my brain operates. Everybody in the first polynomial has to be multiplied by everybody in the second. So I focus on the x squared, and I take x squared times everything in the second, and then I move on. So x squared times the x is x cubed. X squared times the y is x squared y. And then I'm done with the x squared, so I move on to the 2xy. And 2xy times y is 2x squared y. And we might as well stack them on top of each other in that fashion because they're both similar terms. And then 2xy times y is 2xy squared. And then I say, well, I'm done with the 2xy, so I move on to the y squared. And this is grade 10 math. This is not what we're doing in this lesson. So y squared times x is another xy squared. And then y squared times y is equal to y cubed. So what do we get? We get 1x cubed plus 3x squared y plus 3xy squared plus 1 y cubed. I want to point something out to you here, and we don't need to, it doesn't need to be pointed out now, but I just decided, you know what, I'm going to. This is x plus y cubed. And if you look at the exponents on the variables, they add to give 3. And that's even true here, because 1x cubed is 1x cubed y to the 0. So the sum of the exponents on the variables is equal to the exponent on the binomial. And it's true over here as well. We have plus 1 x to the 0 y cubed. And while we're at it, I can point out to you that in the first term, the exponent on x is the exponent on the binomial. And then the exponent on x falls off by 1 each time until we run out of exponents on x. And the exponent on y goes up 1 time, up 1 every time until we get to the maximum exponent. So there's a pattern here, and that pattern is true here as well. Right? This is x squared y to the 0, 2x to the 1, y to the 1, x to the 0, y squared. The exponents add up to 2. Here, the exponents add up to 1. It gets a little clunky in trying to find a connection to all this when you have x plus y to the 0. Basically, it's 1x to the 0, and you've already run out of exponents, so you're done. Let's take a look at Pascal's triangle. That highlight there is only there for me. You probably wouldn't even notice. It's a grammatical thing. It should be plural in your notes. It's an array of numbers that it turns out has dozens of applications in mathematics. Discovered, or, well, not discovered, not fair. Credited to Blaise Pascal. The ancient Chinese used this. It wasn't triangular in shape. It was organized a little bit differently. I would like everybody to try to figure out how you get a row of these numbers from the row above the row we're trying to find. So in other words, imagine that I didn't tell you these numbers. I mean, clearly it's some kind of pattern, and clearly every row starts and ends with 1. But how many of you see how we get the number below by looking at the row above? What are you doing, Craig?
You add the 2 at the
Exactly.
above, to the left.
You look immediately above the number you want and you add the 2 above. So if I want to know what number goes here, it's 20 because 10 plus 10 is 20. So visually, this is how the Pascal's triangle is being created. I used to, when I would teach the binomial theorem, rely on Pascal's triangle a lot, and I've decided this year I'm just going to make a connection to Pascal's triangle and then we're going to forget about it. We're not going to use it. But I still believe that there might be the odd student who will want to rely on Pascal's triangle, even though it's going to make your work very difficult. Okay. Complete the information to the right of Pascal's triangle. And it says above, but it's in a different orientation in your handout. Use your understanding of the connection between Pascal's triangle and binomial expansions to write the expanded form of x plus y to the 4. What are we talking about here? Well, this first row, I don't even need to do that. This first row, everybody, is x plus y to the 0, isn't it? The second row is not x plus y to the 1. But the coefficients of the second row are the coefficients of x plus y to the 1. Because when you expand x plus y to the 1, this is what you get. the third row is not x plus y to the 2, but it's the coefficients of x plus y to the 2, because when you expand x plus y to the 2, you get that. And for those of you that might rely on Pascal's triangle later, I don't really want you to focus on this, but you will notice that the exponent on the binomial matches one more row than the exponent. The coefficients for the expansion of x plus y to the 2 are found by looking at the third row of Pascal's triangle. When we expanded x plus y cubed, we got 1x cubed plus 3x squared y plus 3xy squared plus y cubed. So this isn't just a fluke with the first few rows. The fifth row would be the coefficients of x plus y to the 4, and it would continue in that fashion. Which is very interesting. So what we are asked to do is expand x plus y to the 4. Well, we look at the fifth row of Pascal's triangle. And I'm going to go through fairly slowly with this first one. It's really not difficult, but we're doing a lot today and I don't want to get off on the wrong foot. That means the first term starts with a 1, which is the first number in that row of Pascal's triangle. It has to contain an x to the 4, because that's what we learned through the kind of warm-up, was that your x exponent is going to match the exponent on the binomial in the first term, and even though we do not need to write it, those two are the same, it will contain a y to the 0. My second term will start with the coefficient of the second number in Pascal's triangle, which is 4. And I'm just going to have one less x and one more y. And again, in about 5 minutes, we are no longer going to be looking at Pascal's triangle to find out these numbers. We're going to be looking at something else, which is easier. Because if I ask you about x plus y to the 11, and you want to use Pascal's triangle, guess what? You got to complete 12 rows of Pascal's triangle to find out those numbers. We don't want to have to do that. Plus, well, the next coefficient of Pascal's triangle, of that row rather, is 6. And we're going to have one less x and one more y. And this continues until you run out of exponents, I suppose. The next number is 4. It's going to contain x to the 1 and y cubed. The final number is 1. It's going to contain a 1, an x to the 0, and a y to the 4. Are you with me on that? And I hope you understand that leading 1 and that 1 at the end do not need to be written, nor do you have to write y to the 0 or x to the 0. Okay? Make a mental note, for what it's worth, that this is x plus y to the 4, but you get 5 terms. You always get one more term than n. Any questions on constructing that? It's a pretty powerful tool, but it's about to get more powerful. It turns out that those coefficients can be found using combinations. Rather than looking at Pascal's triangle, and I want you to focus your attention up here, okay? That is 4 choose 0. I don't think you need your calculator to convince yourself of that. If I have 4 people and I'm not going to take any of you for ice cream, there's one way I can do it. I walk out the door, right? This number is 4 choose 1. This is 4 choose 2. And you can verify these with your calculator if you like. This is 4 choose 3 and this is 4 choose 4. This is interesting because of 4 items, there are 5 different ways you can choose things. You can choose none, 1, 2, 3, 4. That's 5, right? And that accounts for 5 terms. So the coefficient of the first term is 4 choose nothing, and then it just keeps going up. So If you want, you can turn the page, because I see some of you starting to write all of this down. It's all written down on the next page. Okay? But the reason I was hesitant in getting you to look at the next page is I don't want you to just read ahead here. I want you to follow along up here. Okay? One of the most important points here is that each of those coefficients is an n choose k arrangement. Arrangement's the wrong word. Combination. Where n is the exponent on the binomial, but each of these is n choose k. 4 choose 0, 4 choose 1, 4 choose 2. And what I'm telling you is n is the exponent on the binomial. So if I ask you to expand x plus y to the 8, the first coefficient would be 8 choose 0, then 8 choose 1, 8 choose 2, etc. So every term has the same n value, but the k value is different for each term. Don't forget, I'm saying that this is n choose k. 4 choose 0 is n choose k. 4 choose 1 is n choose k. These are all n choose k, which means they have different k values. The first term has a k value of 0. And this is the most important thing so far, I think, is recognizing that the identifying, I call k the key number. The key number for any term is 1 less than the term number. So if I'm ever after the 5th term in an expansion, I need to say k is 4. The second, so that's k. The second term has k equal to 1. The third term has k equal to 2, k equal to 3, k equal to 4. So they all have different key numbers. N is like a constant for all the terms, but it's like k is a variable. Each term has a different k. The exponent on y, and this is really interesting and important, the exponent on y is k. K is 0 in the first term, y is to the 0. In the second term, k is 1, y is to the 1. K is 2, k is 3, k is 4. So this number that we're choosing out of n will always be the exponent on y. This lesson so far is about patterns. Okay? Finally, the exponent on x has a value of n minus k. I'm not going to highlight anything here. If n is 4 and k is 3, the exponent on x is the difference between those two, because the two exponents have to add to give 4. And I would suggest to you that that final point, that's all it means. Your exponents have to add to give n, which is why you take n minus k, which is the exponent on y, to get the exponent on x. Expand x plus y to the 5. Well, n is 5. So your first term will be 5 choose 0, because the first term has a k value of 0. It will contain a y. Look at how I'm building this. It will contain a y to the 0 because k is 0. And it contains x raised to an exponent that gives us a total of n, which is 5. Well, that means it's to the 5. What's your next term? Your next term will be 5 choose 1. And you know what? Everything I've said so far about k being 1 less than the term number and the exponents adding up to n, you don't need that at this point in time. It's going to be x to 1 less, y to 1 more. Then this number here is going to go up by 1 each time. So the next term will be 5 choose 1. It will contain x to 1 less, y to 1 more. By the way, since this is, whoops, 5 choose 2, my mistake, x cubed y squared. And by the way, I saw that immediately because one of the things I'm going to tell you is you're always checking to make sure that your k in the n choose k matches your exponent on y. We're going to have 3 more terms because this is to the 5, which means we get 6 terms. The next term will be 5 choose 3. X to, if you want the rule here, x to the difference between 5 and 3. Y to the 3. Then 5 choose 4. X to the 5 minus 4 is 1. Y to the 4. Then 5 choose 5. X to the 0. Y to the 5. So let's clean this up. We are going to need to know what all of these combinations are equal to. 5 choose 0 is 1, and we have x to the 5. 5 choose 1 is 5, and we have x to the 4y. 5 choose 2, I want to say 5 choose 2 is 10. X to the 3, y to the 2. The next one is 5 choose 3. Well, going to your question earlier, if 5 choose 2 is 10, 5 choose 3 is 10. Because every time you choose 2, you choose not to choose 3. So this will be 10x squared y cubed. Then we're down to 5 choose 4, which is 5. It's x to the 1, y to the 4, and finally 1, y to the 5. I always, it doesn't matter whether I'm teaching or working something out on my own, I do the following checks. Do my exponents add up to 5 in each term? They do. Do I start with the highest exponent on x and it's dropping by 1 each time? Yes. Is my y going up by 1 each time? Yes. Any questions with example 1? Example 2, what is the 5th term of that expansion? So in this expansion, n is 7. But here's what I'm going to do now. I have to be adaptable. We've learned about expanding x plus y to the n. I'm going to do the same thing, but my x is really 2x. And my y is really negative 3y. Because the rules I've developed are for x plus y, I'm thinking of this as 2x plus negative 3y to the 7. And I would like somebody to let us know, what is k in this question? Why is it 4? Right, we're after the 5th term. We want to know the 5th term, which means the key number is 4. We remember that. It's 1 less. So I was very careful in how I asked my question. I'm not saying k is 4 for this whole expansion. K is equal to 4 in this question because we're asked for the 5th term. So what will the 5th term be? Well, it will be n, choose k. It's going to contain my x, which is 2x, and my y, which is negative 3y, and the exponent on y will be k. These two numbers are always the same. And the exponent on x, you can either say it's 7 minus 4, which is 3, or you can say, well, it's 3 because the two exponents have to add to give 7. And what I want us to do here is rewrite this in the following way. 7 choose 4, 2 to the 3, negative 3 to the 4, x cubed y to the 4. I'm just pointing out to you that when we have 2x in brackets raised to the 4, that means 2 is raised to the 4 and x is raised to the 4. So I've separated the numerical parts with the variables to impress on you that this is the coefficient. The coefficient of the fifth term is not 7 choose 4. It's 7 choose 4 plus some other stuff that comes out with the x's and y's being raised to exponents. So that's what you need to do for me now. You need to figure out what 7 choose 4 multiplied by 2 cubed multiplied by negative 3 quantity to the 4 is. And it's bound to be a fairly significant number. It's not a tiny number. I'm getting 22,680. Good stuff. So the fifth term is equal to 22,680 x cubed y to the 4. I mean, had I asked you yesterday, what is the fifth term when you take 2x minus 3y raised to the 7? You would have just said, I'm not going to do it, right? I mean, you would have said, is that what we're doing in Math 30? We're just going to grind away at that problem for an hour because that's how long it would take you and probably get it wrong anyway, make a mistake somewhere? No. Now, I want to point something out to you. Do you agree that in this term, k is 4? Okay. Do you agree then that the fifth term is the k plus 1th term? Okay. It's weird, but I'm about to show you the formula that's on your formula sheet, and people go, they recoil in horror from the formula. And what I will tell you is you don't need to use the formula if you understand the relationship here. But the formula is that. This is saying everything I've told you. That if you want, say, for example, the 8th term, what value of k would make this 8? 7. So 7 goes here and here and here, and whatever n is goes everywhere else. If that formula bothers you, you don't need to use it. But you do have to remember the relationship between things. All right. What is the 6th term of this expansion? Well, n is equal to 9. My x is equal to 3x, and my y is equal to negative 1 over x squared. Why not? Why can't we have a binomial that has x in both parts of the binomial? And this is for every term. It's for every term. But since we're after the 6th term, we're going to use k equals 5. So the 6th term will be n choose k. That will be 9 choose our key number, which is 5. It will contain an x, which is actually 3x, raised to, see, I might think of it this way, raised to, I'm not going to worry about that exponent just yet, y raised to the key number, and then what number do I put here so that it adds to 5 to give 9? 4. How many of you would have just said 9 minus 5 is 4 to begin with? That's it. The rest of this question is just basic math. I'm going to again rewrite this as 9 choose 5, 3 to the 4, negative 1 to the 5, and then it's x to the 4, and it's 1 over x squared to the 5. So I hope you understand that all I'm doing is I'm separating the coefficients from the variables. So what do we have for variables? Well, x to the 4 is x to the 4. 1 over x to the 2 to the 5 is x to the 10. On the bottom. Right? When I take the x squared on the denominator raised to the 5, I get x to the 10 in the denominator. Our coefficient is going to be negative because negative 1 raised to an odd exponent will be negative.
Sorry for the interruption. Will the driver of a red Mazda with license plate CDX 8569, that's CDX 8569 is the little red Mazda, please move your car, it's blocking the construction entrance. And so please move your car. Thank you.
I was distracted there. I apologize. Can anybody confirm that you get 10,206? And it's negative, by the way. It is. So the only thing left is to cancel some x's here, right? And you could write times 1 over x to the 6, or you could write negative 10,206 over x to the 6. Now things pick up a gear. If you were to expand this out, and for goodness sake, don't expand it out to answer the question. If you were to expand it out, it turns out one of the terms would have b cubed in it. And I hope you understand that because x has b squareds in it, and y has over b's in it, that they're going to come together in a variety of different ways in each term of the expansion. And what I'm saying, for example, in the previous question, it turns out that the sixth term ended up having over x to the 6. There's no way you could have known that. It's a coincidence that they're both 6s. You can't know it. So let's make a list of what we do know. We know n is 9, and we know x is b squared, and we know y is negative 3 over b. And my question for you is this. If we want to find the coefficient of that term, and basically then we're told that this term is some number times b cubed, right? If we want to find the coefficient, what important piece of information are we missing? Jay? K. We need to know the term value, the term number, so we can know what k is. If it's the fifth term, then we're going to have to use k equals 4. So we need to know what k is for this term. Or we need to know what the term number is. We need to know where in the list this term is. And maybe tomorrow I will show you an algebraic approach, but I find that everybody will benefit by, I'm going to call it a tabular approach. And I'm simply going to construct a table of values, or a table here, where I'm talking about the term number, and I'm talking about the variables. This will become clear. So when I talk about term number 1, what are the variables in term 1? Well, we know that term 1, and this is kind of scrap work over here, but if it's a written response, it's not scrap. The first term is going to be 9 choose 0, b squared to the 9, negative 3 over b to the 0. My question to you is, how many b's will that have when I simplify that? And it will have b to the 18. Do you see that? So the first term does not contain b cubed. Well, okay, it's not the first term, so k is not 0. The second term will be 9 choose 1, b squared to the 8, negative 3 over b to the 1. And I would like everybody to think about why this is going to have b to the 15. I'm not asking you for a deeper reason. I'm asking you, do you see that when I simplify this thing on the bottom right of the screen, I get b to the 15? Because I multiply these exponents, 2 and 8, to get b to the 16, and this will be over b to the 1, so I get b to the 15. Now, the deeper question is this. How many of you understand why this exponent count has dropped by 3 in going from one term to the next term? What's happened is we've lost one of these. So we've lost 2 b's right out of the gate. And we've gained one of these. But one of those is divided by b. And what I'm getting at, we can do the third term if you like. The third term would be 9 choose 2. It would contain b squared to the 7 and negative 3 over b to the 2. And if you say b to the 7, b squared to the 7 rather, that's b to the 14 over b squared, well, that's b to the 12. And what I'm saying is we've established that b drops by 3 each time. And that means we can complete the table and say this will be b to the 9, this will be b to the 6, this will be b to the 3, which is what we're after. That's what the question says. So this is the 4th term, this would be the 5th term. We are after the 6th term, and now we know k. Now we know k is 5. And we can answer the question. Everything we did so far is simply to identify k. So the 6th term will be 9 choose 5. It was to the 9, wasn't it? X, which is b squared raised to the 4. Y, which is negative 3 over b raised to the 5. If I separate out the numerical pieces of this, it's 9 choose 5, it's negative 3 raised to the 5, and I have a b squared to the 8 times a 1 over b raised to the 5. Not to the 8, to the 4. The really nice thing about this, let me finish my writing and then I will give you my thought. The really nice thing is there's so many internal checks and balances here that I was automatically looking to make sure that I would get b cubed, and b to the 16 popped out of somewhere. I knew it couldn't have been an 8, so it's a 4. Give this some thought. Does this reduce to b cubed? Yes? This is our answer. Whatever 9 choose 5 times negative 3 quantity to the 5 is, that's the answer to this question. Anybody else for that number? Okay. Negative 30618. So the 6th term is negative 30618, b cubed. So the coefficient, the answer to the question is just that number, negative 30618. Once again, with this question, your primary objective becomes, what is k? I need to know what k is. And then it's like the previous questions, which should be easy. I am going to skip over the next example. Well, I won't skip over it. I will talk about the next example here. If I say to you, which is the constant term in this expansion, I'm telling you that there will be a term that has some coefficient times x to the 0. If we have time, and I don't want to crowd this lesson, I want to give you some time to work on this stuff. We will come back and do this question, but in the end, you're going to do the exact same thing we just did. You're going to find out how many x's there are in the first term and in the second term, and based on that, figure out which term will have no x's so that you can use k to find the term. Okay? But let's go to the ultimate question. This is probably the hardest question. I don't mean to make it sound like it's really difficult. It's not. It's just that of all of these, it's the one that I think students struggle with the most. The problem here is, if we make a summary of what we know, n is 8, x is actually kx, and I hope you understand what I'm saying when I put those quotes there. That this is our x in our template. Y is negative 6. The problem here is we know a term. We know that term. We're not trying to find it, but we don't know k. And listen, I can't avoid it. If I avoided this all the time, I'd be doing you a disservice. I hope you understand that the k that we're trying to find, that's the coefficient of x, is not the key number of this term. Right? It would be nice if the world was kind to us all of the time and did something like this and said, find a. If you need to do that to work through a problem, then do so. But we're dealing with k here, which is a coefficient of x in here. And over here, there is k, which is a key number of some term. We still need to find out what the key number is. We need to find out which term this is. Is it the first term, the second term, the third term? So we need to find out which term has x cubed. That's all. The first term, I'm going to present this to you in a different way this time, will contain kx to the 8. I am not saying the first term is kx to the 8. I'm saying it's going to contain that, which means it's going to contain x to the 8s. My second term is going to contain kx to the 7, and, well, you know what? It's going to contain kx to the 7. Who cares about the negative 6 to the 1? Because there's no x's in it. It's going to contain x to the 7. Oh, okay. So which term will contain x cubed? Well, we can just continue this pattern. I'd be very cautious about counting this off in your head. It'd be very easy to make a mistake. So the next would be x to the 6, then x to the 5, then x to the 4, then x to the 3. So this is the third term. This is the fourth term. This is the fifth term. This is the sixth term. This thing that we were given is the sixth term. Which means our key number is 5. And that means that this negative 224,000x cubed is equal to 8, choose our key number, times x, which is kx, raised to the difference between n and the key number, times y to the key number. Cleaning this up, by separating the constants or the coefficients from the x's, we get that. This is why it works. The x's cancel. You can find k. I'm going to take negative 224,000. I'm going to divide it by 8, choose 5. I'm also going to divide it by negative 6 raised to the 5. And let's convert it to a fraction because why not? 125 over 243. Because 125 over 243 is not a perfect cube, by the way, this would probably be a numerical response question. So what is the value of k to, say, 2 decimal places? Well, we just need to take the cube root of that, which I'm going to raise to the 1/3 to do. It's approximately 0.80. So there are 2 parts to this lesson. If I give you anything that looks like that, I should be able to get you to find any term. I should be able to get you to find the 5th term or the 8th term. You should also know there will be 13 terms, okay, because it's to the 12. And the other aspect is finding a term where you're after a term where it's, say, it contains x to the 12, and you have x's in each part of the binomial. So I'm not going to go back and finish that other problem. I don't want to drag this out any longer. I think you get the idea. You need to work hard at this. It's different than combinations and permutations. The only thing that connects is that NCK.